So we'll start with announcements. Have two projects and an assignment due tomorrow, and we have a final next week. That's basically it. There's not very far to look ahead anymore. So our final review will be tomorrow. Today is the last day of content. Since there's not a ton of content here, what I assume we're going to do is just get through the last little bit of it and see what people would like some extra practice with ahead of tomorrow's review when we actually go through a bunch more problems. So for LR parsing, let's refresh ourselves on exactly what this gross diagram was and everything that was happening here. So we had this concept of items and closures. So we have states with a bunch of items. And this is just a production with a dot somewhere in the production. As we either shift or reduce, we're going to be moving in this DFA. With shifts, we are going to be moving forwards, and with reductions, we're going to be moving backwards against the arrow. As we do this, we will eventually reach a final state. The final states tell us that there is a reduction that we can do, but the real final state is once you've moved past the S prime arrow S in Q1, you know you can accept because we are past that initial S from the grammar that we started with. So we defined this whole process starting at the start state, repeatedly applying shift and reduce operations. This is a DFA now, so there should only be one possible move. It's not an NFA. There's only ever one thing that we can do unless we're in the process of a reduction where we moved backwards and found that there were, for instance, from Q4, there were two backwards arrows. Actually, there are three backwards arrows on a B. We could move from Q4 back to Q0, Q4 back to Q4, or Q4 back to Q2. That's the only place where we don't know, so we have to store something about where we came from. And you can either attach that to the object that we put on the stack, so that when you pop that off the stack, you know where you came from, or you keep track of a separate data structure that keeps track of a history of states that you've visited. And then you can query that structure to figure out where did I come from to get to where I am. So those would be the two reasonable ways to solve that issue. So shift moves forward and a reduce moves backwards. So this is just all of the logic that I just went over. But that's basically what it is. Do either of you have questions on this process? So, all right. So let's go through a full example. So the most recent grammar and DFA. So we're going to trace the acceptance of ABCAB. We also want to show the entire parsed stack. So information that you're going to want for this, let's actually write this out. What are you going to be annotating? We need a stack history. So this is just going to be, stack, 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 as you show the history of what's on the stack over time. Then you also want the current state in the DFA. Beyond that, you need to know what character you're looking for. So your one character look ahead, because remember this is LR1. So what character are you looking for? And then finally, what is the action that we're taking? And it's either a shift or a reduce. So we know that in the stack history, we're going to start in state Q0. The first character we're looking for is this A. So the look ahead will be A, and then the action we're going to take when we do this is going to depend on, I'm going to go back and show you the DFA. It's going to depend on what consuming an A looks like in that DFA. So I don't want to, I did go far enough to the right. So when we read an A from Q0, there's only one output from that, which means that we go from Q0 to Q2. Because we built this DFA already, we don't have to worry about how any of the items change. We just know, excuse me, all the updated items of where we could be in the grammar once we arrive in Q2. So we know that consuming the A is a shift, it's not a reduce. So go ahead and fill out the rest of this table. Now we have the bottom of stack character followed by the S that we put on there. There'd be one to put the S on there. And this is going to put the A on there. Or cab. How's it going? Anyone have questions or problems getting started?
Oh, it's, I guess I'm just kind of confused.
Yeah.
We have an S in the tag. Reading that in, where would we go use it like, because, if we take the S from Q0, go to Q1, and then we have. I'm not really sure if you do that, honestly. I don't think I'm going
Yeah.
the right way.
Yeah, so we're not reading the S, we're reading the next aspect, the next character in the string.
I see.
So we can't do this until we can move past this S. Like, can we pop the S off the stack at this point? So if we were to go directly S prime, there's no S prime on the stack.
Okay.
Once we have an S on the stack, we can move past that S. Or once we have resolved this, then we can move past it. We should start by moving to Q2, reading the A. That should. That looks confusing. We'll get it. We would push an S onto the stack, we were doing LL parsing. Because we're doing LR, there's no S on the stack. We have to make the S. Honestly, this should actually. Here's kind of the first. Everything that makes sense so far?
Yeah, that step was what I was missing. So putting the A on the capital A on the stack.
Yeah,
Yeah. That's
yeah,
what I
when we
was.
move past it like this and then we reduce on the way back, this A goes on the stack.
Gotcha. I was like, so like keep
In
five
place of
miles.
the C.
Yeah.
Yeah. Next one. Space. This is wrong. When we did this B, we didn't move to Q5. We moved from Q2 to Q4. So when we read the A, I think it's because of offset here with the action. We want to shift the A on. When we shift the A on, we're no longer in Q0, we're in Q2. When we shift the B on, we're no longer in Q2, we're in Q4. So the backtrack from here is not Q2, it's Q4, which makes it possible for us to take this B AA and move from Q4 to Q7 and Q9 back. That's the issue. So this reduce, bring this back to Q4. And since we do a reduce, we shift the A on, so we should actually not be in Q4. We should be in Q7. Because if we look at the algorithm, when you do a reduce, you shift all the way backwards to where we were, but then you have to reduce back to where we were, but then we have to shift the A that we just put on there. So that should put us in Q7. Then we read the A and we're in Q9. Once we successfully put that on, okay, it's going to be B. And from here, we actually want to reduce. So this BAA, if we're doing this in reverse, if we were storing where we were coming from, we're going to do this reverse order. We're going to go backwards, the A, the capital A, and the B. Where did we come from when we put that B on? We went from Q2 to Q4. So we're going to go backwards all the way to Q2. And that BAA produces what? Produces an A. So we're going to back all the way to Q2 and then shift on that capital A, which puts us in Q3. So the next state is Q3. We're still looking ahead to that B. But we need to reduce again to get there, because we need to move past this A. So this state of this stack is now bottom stack character, the A. This has all been replaced with an A, which we moved to. And now we need to consume that A so we can turn it into an S. So here we're going to reduce again. So as we do this, we go back to Q2, but now we need to consume the S and go to Q6. We'd be in state of Q6. After this, look ahead is still a B, but now it's time to shift that B on, because there's no reduction that we can do. That's the next thing that we are looking for, is that B. So we're going to shift that B onto the stack. So putting that B puts us in Q8, so we're in state Q8. Having read the B, the look ahead is now the end of string marker, the dollar. And the action from here is that we can reduce. Since we're in a final state, we know we can reduce that, so we're going to backtrack off the B, the S, and the A. The B, the S, and where did we come from when we read that A? We came from Q0, all the way back at the very beginning. That's gonna take us all the way to Q0, and then this reduction leads us to an S. So we're going to move forward on the S path, which is gonna put us in state Q1 with the stack Z and just S. We get the end of string marker, and from here we can basically move in the NFA. We basically accept here. I would just say that the goal is to reduce off the S and take it away. Since we ended up in Q1 with an empty stack with just the S on the stack, we reduce back to Q0 with nothing. So reduce Q0 dollar, and the action is to accept at this point because we just have the bottom stack. You can either stop on Q1 or stop on Q0, whichever one here makes the most sense. Both of those are fine. But the idea is we got an S, we got the S off the stack, it's now empty. So this tells us the string is in the language. Questions on that whole process? I'll bring up the book's solution so we can talk about that as well. So if we go all the way to, there it is. This is keeping track of the states that they came from. That's why these numbers are there. We did that kind of separately and off to the side, but you can show that the states that you come from when you make a transition can also be pushed onto the stack. You can also keep track of that in a separate structure, but other than that, this should be exactly what we did. In order to figure out where we came from, we did a shift, 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 reduce, shift, reduce, shift, reduce, accept. Because we ended up with a look ahead of dollar in state 1. They don't backtrack to state Q0, they just accept from 1. So this is a final state, we move past this S. If we ever see the look ahead dollar in state Q1, because of that's what got us past that S prime arrow S that we added as a production. When we get to that point, we can accept. So I also have some text from the book here that explains exactly what this diagram is doing. It should be exactly what I just mentioned. But in case you're looking back studying, maybe this would be useful. Questions on this? Process make sense? Until it doesn't. So each final state only had one item, which could be a reduction. But of course, you could have a final state with multiple items. If this were the case, then you would have an option of a shift or a reduce at that point. That would turn this into an NFA rather than a DFA, or the concept of an NFA, we still have to choose between that shift and a reduce, so we would need that parallelism to be able to solve the problem in linear time. But if you end up with a look ahead, kind of like we did with the LL, we can have an LR of K where we could do a look ahead to determine, is it possible for us to know whether we should shift or reduce based on that look ahead? If the look ahead can determine, should we shift or reduce, then we end up with an LR2 or LR3, LR10 grammar. Because that look ahead can remove that ambiguity. In this example, there was no ambiguity, which showed that it was LR1. With a look ahead of 1, we were able to determine, should we shift or should we reduce? Because inherent in that DFA, there were no options. Look aheads can help, but not in all cases. If lambda is involved, then look aheads can turn out to be, we end up with no such K that we can have an LRK grammar. And if we can't have an LLK grammar and we can't have an LRK grammar for a particular grammar, then we have to default to using CYK. No linear time algorithm will exist that we know of. So we have to default to that cubic complexity CYK. And that is the entire curriculum that I have prepared for this class. Right? We reached the end of it, basically on the last day, or close to the last day, which is nice. So I can spend the next 20 minutes going over any examples, anything that would aid in the clarity of either of the projects or the existing homework. If any of you have some such something that I could do that would be useful. So Daniel, you mentioned before that another LL example would be useful.
Yeah,
Would that still be the case?
probably, yeah,
Let's do that.
if you have one.
I haven't prepared one, but I can go to either the homework or the book to find something. Let's start with the homework. But I don't think there were options of things that were there that were not assigned. Is that right?
I think there was a bunch extra that were in there that wasn't assigned. Actually, at least a few.
Yeah, so
Remember you looked somewhere that. Didn't have a good example.
it's not here. Let me go to the book.
Like determining what A actually works for. I think.
Yeah, if you just ask us to explain why LL1 doesn't work, do you want us to find which value of K would, or is that kind of?
No, if the question was exactly, is this LL1? All you would have to show is there is a conflict in the LL1 table.
Gotcha, cool.
If I asked for which K is it, then you could construct the LL1 table and say it's LL1 because there are no conflicts in the table. But if it asked for the value of K, then you would have to use some kind of look ahead.
Go from there. Gotcha.
Yeah, to say that. So for class. Go. I rechecked this out literally yesterday. Maybe I can directly go through the homework problem. Is there anyone that we are stuck on that I can help with, or one that you'd like to verify your answer to? So I think we're starting with 16.1. We could start with the LL parsing process. So 16.1, number 3, 16.2, number 3, 16.3, number 2. Any of those.
I think that would be 16.1.
Yeah. Okay, so that says consider the grammar where we have right up here. This is very big. Let's see if we can blow it up a bit. All right, people can kind of sort of see that, I think, maybe. How is it remotely? Kind of gross. So, all right, construct the equivalent DPDA that models the LL parsing process. So what did we do for that? Who can recall the process for constructing an NPDA based off of a context-free grammar that models the LL parsing process? How many states? Three states. So we have a Q0, we have a Q1 where all of the work is going to happen, and we have a final state Q2. Excellent. The purpose of Q0 is to put the start non-terminal on the stack. So this is just going to say we're going to move into Q1. All we have to do is say we are not making a change to the string. We are not popping anything. And we are pushing SCD. So we're putting S on the stack. Great. In Q1, now we need to figure out what are our possible transitions. So what were those two different transition types?
All the productions and then all of the reductions.
So we need to be able to produce and reduce. I did not plan. So all of the possible productions, say we're going to basically pop the left-hand side and push the right-hand side. So we would need all sorts of transitions associated for that. That's kind of gross. Don't know if I want to draw that. But we probably should. If I'm assigning it to be able to do it in class. The issue is there are 6 of them. So maybe I'll give you a few of them. So here we're going from Q1 to Q1. We're making no change in the string, but we're able to make no change in the string. We're going to pop an S and we're going to push an ASB. And you can do the same thing. We're making no change in the string. We are popping an S and we are pushing CA. Continue to do this for every production. And then what was the second potential production?
Reading the kernel when off the terminal. Yeah,
So we're going to have some transitions that allow us to, now we do want to make a change to the string. If we see an A on top of this in the string, and we see an A on top of the stack, we can pop that A and move forward in the associated string. So if what's on top of the stack is a character, and that character is what we are looking for, then we can get rid of it. So we would do that for every terminal. We would do this for every production. And that becomes everything that we could use to do that. Finally, how do we get to state Q2?
We have nothing reading and we're at the bottom of stack character.
Yes. So we're going to make no change to the string because we are already there. The bottom of stack character needs to be what's there. So we need to be able to pop the bottom of stack character. And of course, we're just going to push it right back on. As part of that, And then if that's all that's there in Q2, meaning that we're at the end of the string, then we can accept. But if there are still characters to read in the string, then there's no transition out of Q2 we would reject. All right, so I think that is A. As long as we have, a loop with a ridiculously long number of here. So use the NPDA constructed and one look ahead in the string, parse the string CCBB. Show the stack contents, the current state in the NPDA, and the current look ahead in each step. So we can do the easy one. The harder one's going to be a little bit longer, but all right, CCBB. So in Q0, we're going to start with just the bottom stack character on. We need to be able to show the stack contents, current state, which is Q0, the current look ahead, the first character we're looking for. And now we can say that, okay, we can transition from Q0 to Q1 and put the S on the stack. We still have a look ahead of a C. What do we do?
Off the S in place of CA.
Yeah, there's no way we'd ever want to put this production on there, right? Because then we'd be looking for an A and we look at here as a C. So the only way we're possibly going to be able to produce the string is through that production. So we're going to follow that transition. Stay in Q1, we're going to have C and we're going to replace the S with CA. And the look ahead now is another C.
Is that upside down by chance? The CA, or is that how it's supposed to go in?
We should, whatever is on the right should be on top. Wait, is that true? No.
Is that what R for a second? Right?
Very wrong. Yeah. So you go from right to left. My bad. So now we can shift the C, which is what we want to do. So we're still pointed at this first C, but we can get rid of this C now as we leave just this A on there. We're still in Q1, and our look ahead is the second C now. We've moved ahead, we've done a shift in the string, reading the first C, moving to the second C. That's not inherent in this drawing, but that's what's happening at this step. All right, well, now we need to do something that is going to allow us to read a C. The good thing they didn't have us do first and follow for this, because we'd be able to tell from the first and follow. But luckily, it's pretty apparent. Which production do we need to apply from A to be able to produce a C? It needs to be that CAB. So we are going to follow that transition. Staying in Q1, we have the Z, but now we're replacing the A with right to left, B, A, C. Look ahead is still a C because we haven't moved past it. We're going to take that same transition we took here to get rid of this C as we read this C in the string. So we're going to pop the C, stay in Q1, move ahead from that C, and look now for a B. How are we going to produce this? Well, we need to resolve this A. Is there a production that we could replace the A with here that makes sense to be able to produce a first character of a B?
Yeah, capital B.
Yeah, capital B. That is exactly what we're going to do. Stay in Q1. Look ahead is still that same B. On this stack, we're replacing this A with BB. All right, how do we turn this B into the very first thing that we're looking for, which is a B? Yeah, we got to get rid of it. We can't apply this because that makes it an A. We can get rid of it, and what we happen to know is there are the two B's we're looking for right beneath it. Of course, our program wouldn't know that, but the only way to remotely get to this is to cancel out the b, turn it into a lambda. So that's what we're gonna do. We're gonna stay in Q1, still on that same first b, but we turn the b into a lambda. It goes away. Excellent. Now we can do the last couple of shifts. We can stay in Q1, read the first b, and that moves us to the final b in the string following that transition that would be right there. And then we can do exactly that same thing again. We're going to stay in Q1, look ahead. Now is the end of string marker because we're moving past this b, and we just have the bottom of stack character. Since we just have the bottom of stack character, this is now a legal transition that we can make. So the final stack that we're going to draw is just the bottom of stack character. We're in state Q2, and a look ahead is the end of string. So this tells us that we can accept. We made it to Q2. The two things that need to be true are true. The stack is empty. We're at the end of the string. Questions on that? That what people got for their answer?
I had a few minor mistakes, but yeah, it's for the most part what I had.
All right. I will do it as an exercise for you to go through this discussing this. Anything with building the LL table? We only have 5 minutes. I can answer any of these questions as well in office hours, or we can save it for tomorrow's class. Either one will work. But we could build something with an LL1 table because we have to calculate first and follow to be able to do that. So maybe we can at least start with the first and follow of 16.2. All right. We're going to have a first. And a follow. For all of S, A, and B. So sad. All right, how do we calculate first of S?
Reduction in C, what are the first non-terminals that would show, or I mean terminals that would show up?
Yeah, we can see what terminals would show up. So A and C. Nothing too crazy here. How about first of A?
First of terminal C and then first of non-terminal B.
Yeah, so it actually makes sense to do first of B first, because with that lambda, we see that we're actually going to include it. So we put A and lambda here. So that when we go look at first of A and we see that first of A is going to be first of B, then we see that this is going to be a C, whatever could be in first of B. So we're going to copy everything from here. And since lambda is in first of B, then anything that can follow that B. So that leads us to say A, C, and this B can be negated, so a B as well. So A, B, and C can all be in A. Now lambda cannot be, because A cannot immediately derive lambda. If A could derive just B and B could derive lambda, then A could derive lambda, but A cannot derive lambda directly. So this is just A, B, and C. How about follow? What can follow an S? We know that the very first thing we do is we add dollar to follow of S. What else is there?
B.
B, yes. Here's the S on the right-hand side, a B immediately follows it. All right, what's going to be the next easiest one to do?
B.
We have a vote for A, we have a vote for B. Fine. let's do follow a. What could reasonably follow an A?
B,
So we have a B from here. Great. What else?
dollar,
Dollar. Because A can end S, anything that could follow S could also follow A. So we just are going to take everything from follow of S and move it into follow of A. We've already seen the B from here, but if we hadn't seen it, then this B would also be relevant to this A, because this A can become that. So we're going to state that we just have B and dollar. Let's follow of A. How about follow of B?
C and E.
So we're going to follow B. We can get a B from here, we can get a C from here. If B is lambda, then what could follow? It actually doesn't matter, because the fact that B could become that doesn't matter. It's the A that could follow an A. If A becomes B here, this B could. Yeah, if there was something in here that could become lambda, then we have to check that. It becomes a nice, but here it's pretty straightforward. So we just have B and C. All right. So we're unfortunately out of time, but the next step would be to build the LL1 parse table. I don't think there's anyone in here immediately following this, so I could just go through and finish this off. Why don't I do that? If anyone needs to leave, you're welcome to leave. I'll see you tomorrow. But I'm going to do the LL1 parse table just so I don't pause this in the middle of the process. So what does the LL1 parse table look like? What are the rows and columns going to be?
And then all the terminals on top plus the end of string.
Yeah, so we have A, B, C, and dollar as columns.
First. Or I guess your rows are gonna be all of the S, A, and B.
Yeah, we'll have capital S, capital A, and capital B. The question is, if we are in any of these, what is the production to apply if the next terminal is going to be one of these? So that is the question that we are answering with this LL1 table. Good enough. Okay. So given all of this, what do we apply if we want to get an A from S? ASB. Great. How do we get from an S to a B? Is that possible to do? Well, we look at first of S and there's no B. So that's going to stay empty. First of S also cannot be dollar. It's not in first of S. Excellent. So C is the only one that's left. It should just be CA. First of A can be A or B or C, so we're going to fill out A, B, and C. What are all of the possibilities for getting an A from here? You have to
BB.
go to the BB and have that BB become ABC. So that production can get you an A in only one way, which is good. How about the B? Go to B, go to lambda, gets you this B. So BB also is the rule to apply if you're looking for a B. If you're looking for a C, on the other hand, you have to apply C capital AB. There's no way for the A to produce the end of string at the start. For B, we see that there is an A and a lambda. So we can negate the B, but we don't actually need to. We also need to refer to the follow when we see that lambda to say what can follow a B, because that could be the first character when we are at that B. So if we're at a B and we're looking for an A, we can apply A, B, C. And since this can be lambdaed to get to B, we would apply the lambda rule because we know we can get there. And for a C, we can also apply the lambda rule to get to Apollo. That was the case here. So if the previous thing had been a C, then the goal would be to take this lambda production. And we're most likely to be able to get a C from there. And we can't produce dollar because this lambda is here. You check the follow. There's no dollar in the follow. So there's no way for what begins a B to be the end of string.
So if S or A had a lambda in the set, then we would refer to the follow, and in that case, we would have something in that column.
Yeah. I think this does it. Questions on producing the LL1 parse table? It is LL1 because there's no multiple production in any one of these cells. So we can, with a single look-ahead character, determine which production to apply.
All right. We're going from more complex back to simple.
Sorry?
It's kind of weird going from complex
Yeah.
LR back to simple with LL.
Right? Isn't that strange? Luckily, I'm not going to throw LR on any exam, so I think there are a couple problems in the homework, but as far as the exam is concerned, you really only need to be able to do LL1, LLK, be able to show that something is not LL of any K.
Have you written up the final bit?
Yes.
How many problems it is? Am I allowed to ask that?
Exactly how many was that? I think I'll find out. I do not remember exactly, but let me go. So in terms of numbered problems, there are 7, but multiple of those have multiple parts. And even some of those parts also have multiple parts. So the total number of questions answered is 21.
This is also 100.
Yeah, and there are, unless I change this is not completely finalized yet. I'm going to do a pass over grades to see if I want to modify the point structure necessarily, but there are 116 possible points, of which 10 are just gimme points.
Thank you.
No, I like it.
Yeah.
Yeah, well, you will get 10 points no matter what.
Is it like a write your name and get 10 points?
Slightly more complicated than
Yeah.
that, but not intellectually any more complicated than that.
Yeah. All right, well,
Thank you.
Yeah, thank you. See you tomorrow for our review. Couple questions.
Yeah.
Oh, yeah, can you make one that's like LLK and then find out what the K is?
Yeah.
Sorry, thank you.
Yep.